Hey guys, this is Garth here again, and I'm back for the last video in this set of tutorials. So I want to give you guys an example of how to do an adder circuit all by yourself. So in the assignment on Moodle, in order to get full credit, you will have to do the adder portion by yourself. So what you'll be doing is you'll be taking this adder chip here, the built-in adder in Logisim. You want to remove this chip and you want to swap it out with your own adder chip that functions the exact same way. So you'll be making this all by yourself, and it's got to be a 32-bit adder chip. And in this video I want to give an example of how to do a 1-bit adder, and then how to turn that 1-bit adder into a 4-bit adder. We'll be chaining several 1-bit adders together, and so from there on it should be pretty straightforward of how to take that and how to make a 4-bit or a 8-bit or a 16 or a 32-bit adder. You can make any number of bit adder after watching this video, and I want to give you guys an understanding of how this functions at a fundamental level. So how the adder circuitry actually works, not just here's the circuitry, go ahead and memorize it and use it. I want to give you guys the derivation for this circuitry, and we'll be driving this circuitry for the adder all by ourselves. So I want to go back to OneNote here and say I want to add some numbers together. Say we're doing this by hand and I've got some 4-bit number. Since I'm doing a 4-bit adder example, say I've got 1, 1, 1, 1, and say I want to add that to 1, 1, 0, 0. So I got these two numbers and I want to add them together. And 1 plus 0, that's just 1. 1 plus 0, that's 1. 1 plus 1, that's 2. In binary, we represent that as 1, 0. So our answer is 0. And we carry our 1. And then I've got my last column here, and I've got 1 plus 1, and I've got the 1 that we've carried from the previous column. So we've got a total of 3 here, and in binary we represent 3 as 1, 1. So our answer will be 1, but we'll also carry a 1. So we'll just bring this last 1 down here, and we've got that listed here. So if I were to ask you to do this in 4-bit binary, you'd expect to have this as your answer, 1, 1, 0, 1, 1. And that would be the correct answer, but if I were to ask you, do this only in 4-bit binary, is this correct? You should say no. Because in 4-bit binary, your answer is just going to be these 4 bits here. And you're going to be leaving off this last bit. This last bit here won't get included in your answer. So you'll actually give me the incorrect answer if I tell you to add these two numbers up in 4-bit. And the CPU, the ALU portion of our CPU, it'll be doing the same thing. It's no different. It's going to give us this exact same answer if we were to feed it these two numbers. If I were to feed it these two numbers in my ALU, and I can actually hold on to this example and try it later and show you, but we'll get an overflow. An overflow will occur. So anytime we try to do 4-bit numbers in 4-bit addition, and we get 5 bits out of it, we know that that's an overflow, and we're doing this math by hand. But the CPU doesn't necessarily know that. It doesn't necessarily know, well, hey, I had 4 bits coming in here, and my answer was 5 bits. That's 1 bit too many. It doesn't know that. It can't count how many bits. How it knows whether there's an overflow or not is it looks at this last bit here, and it sees that it's 1. So this last bit here is our overflow bit. And it'll make sense in a second how this ties into the circuitry. But we essentially want to look at this. If it's 0, it's alright. If it's 1, it's an overflow. And you might say, well, how does it know if it's 0? Well, remember, if we're doing math in just plain decimal, and say I've got a number 15, well, that's perfectly equal to 0, 1, 5. So if I were to say 0, 1, 5, that's equal to 15. So we've got the same thing going on in binary. So behind the scenes, when I give you this answer, if I were to come out with something like 0, 0, 0, 0, 1, 1, well, that would be perfectly equivalent to just 1, 1 by itself. These would be two equivalent answers. So if we didn't have this overflow bit here, we would just assume that that was 0 by default. So we've got this 4-bit addition going on, and I want to break this up into individual columns. We want to modularize this. I said we wanted to make a 1-bit adder circuit, and then we want to chain these together. So we want to modularize this into 1-bit addition. So say I've got 1 plus 1. That's 2. So this is number A. This is number B. And I've got some output. And then I've got the answer. So 1 plus 1 is 2. So that's 1, 0. Technically, if we had multiple columns here, this 1 wouldn't get shown as the answer. It would get brought in to our next column. So we call this the carry out down here. We say this is the carry out bit. So this is our answer bit for this column here. This is our answer bit. And then we've got our carry out bit. And so this carry out bit gets brought into the carry in bit for the next column. So notice here in our 4-bit expression, we had 1 plus 1. We got 2 as the answer. We got 1, 0, 2. That's our answer. So we've got 0. That gets written down as the answer. But we've got a 1 that was carried out. And we got it brought up here to our next column. And the carry out bit for this column became the carry in bit for the next column. So that's the carry out. So any given column could have a carry in. So it's important to notice that this was the only column that we carried anything in for. But we could have very well had a carry in for any of the other columns. We just had a carry in of 0 here. We had a carry in of 0 here. And a carry in of 0 here as well. We just didn't label it. But internally, we can think of that as being 0. So when I say I've got 1 plus 1, and I want to do that in binary, A is 1 and B is 1, and I want to add them together, and I get 2 as the answer, I'm actually carrying in 0. So I've got this number carry in. So I've actually got 3 inputs here. I've got our carry in input, our A input, and our B input. And I've got 2 outputs here. I've got our output answer, and I've got our carry out bit, which gets chained into our next column for the carry in bit for that next column. So this is kind of how we modularize our arithmetic here. We've got 3 inputs and 2 outputs. And if you go into Logisim, you'll notice that the chip matches. We've got A, B, we've got our carry in, we've got our carry out, and then we've got our answer. So if we go back to Logisim, and we look at our built-in circuit, we've got an input, another input, we've got our output on this side, and then we've got this funky carry in bit, and then we've got this other funky carry out bit, and now we know what those carry out bit and carry in bit do. So we can go ahead and we understand fundamentally how the mathematical expression works in terms of inputs and outputs. And now what we want to do is we want to convert this into a truth table. And then we can go ahead and take that truth table and we can convert that binary truth table into a sum of products mathematical expression. And then we'll take that mathematical expression and then we can convert that into a logic circuit. And so I've got a separate video on that I've already uploaded for how to take a binary truth table and convert that into a sum of products expression and then finally into a circuit. So if you haven't watched that already, I'd encourage you to watch that first. That's kind of a prerequisite for this video. So for our truth table, for the inputs we want to have, so we've got our truth table for a 1-bit adder. So I've got an input A, an input B, and then I've got our carry in input, and I've got our carry out, and then I've got our final output. And so like all truth tables, we want to cover all possible combinations of inputs that we could use here. So we want to make sure we've got all of our inputs covered. So since we're dealing in binary, this is base 2. We can have 0 or 1. That can be our input combination. Since we've got 3 inputs here, we say that we have 2 to the power of 3 possible inputs. We've got 8 total possible inputs here. And we've got this 2 here because this is binary, base 2. We've got 1 or 0. That's what we could have for an input. and then we've got 3 here because that's the number of total inputs we've got. So we can actually count in binary and write these out. I've got 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and 1, 1, 0, and 1, 1, 1. And so if we count these up, I've actually got 8 rows here, and so I've got all of our inputs covered. I've got all 8 input states covered for the combinations of A and B and carry in. And now I want to go ahead and convert this and figure out, okay, I've got our A and our B, and I've got our modularized expression up here. Now what happens in our circuit? What happens for what's the carry out and what's the output for each of these combinations of A and B in our carry in? So I can go ahead and take these input and put them into a mathematical expression. Say I've got A plus B. I've got 0 plus 0, and I've got this carry in bit of 0, and so that's up here. And I add this all up, and I've got 0 as my answer, and that's my output. And then our carry out bit, that's 0 as well. I'm definitely not carrying anything if I'm adding up 0 and 0 and 0. So our carry out bit, that's 0, and our output bit, that's 0. So now I've got this row done for A and B and our carry, and I know what the outputs were. And so I want to do this for each row in our column. And so if I've got A is 0 and B is 0 and our carry input bit is 1, I can go ahead and write a mathematical expression for that. So I've got A and B, and I add them together, and I got a carry in of 1. And I add this all up, and I get 1 as the answer, and that's my answer. So 1 is my output answer. And then I look and see, well, do I have a carry out? Well, no, I don't. I'm only adding up 1 here. The answer is just 1. I don't have anything carried out, so I just got 0. That's my carry out bit. So I write that down. And you can go ahead and save some time and look at the combinations in the circuit where I'm only adding up 1 here. Since fundamentally, whenever you're adding up 1, it doesn't matter if A happened to be 1, or it doesn't matter if B happened to be 1, or if the carry-in bit was 1. If the sum happens to be 1, it's going to be the same. So for example, if we look at this and we say, oh, this happened to be added up to 1, well, we can look at all the other cases in the circuitry as well. So this happens to add up to 1, and this adds up to 1 as well. So we know that if we wanted to save some time here, we would know that the carry out and the output bit are going to be exactly the same. So I could copy this down, and I say the carry out is 0 and the output bit is 0 in all cases where I add things up and I get a 1. And so now I could look at this column right here, and I could say, oh, I've got A is 0 and B is 1. So I got A and B, and I add them up together, and then I've got a carry-in bit of 1 up the top here. So I add these together and I get 2. So I write 1, 0. So my answer is 0, and I have a carry out of 1 that gets brought to the next column. So my answer, that's 0. So my output 0. And my carry-in bit up at the top, that's 1. So I write down a 1 here. So again, I can look at all the cases in our circuit expression where, since we're just doing addition here, this isn't true for all truth tables, but it is for our case, since we're fundamentally just adding up A, B, and C here. I can look at all cases where we come up as 2 as the answer. So I could say, well, this is 2. And I could say, well, this adds up to 2 as well, 1, 0, 1. And this adds up to 2 as well, 1 and 1 and 0. So I can go ahead and copy this expression down. 0 is our output and 1 is our carry output bit. I can go ahead and copy that down to the other cases. And so this saves quite a bit of time and when we're filling out our truth table here. And I've got brought to our final answer, our final case here, when A and B and our carry-in are all set to 1. We want to figure out what the answer is in terms of binary. So I have A and B, and I add them together, and I've got a carry-in bit coming in from some previous column, and then happened to be 1. And I add these up, and I get 3. And so 3 in binary, well, that's 1, 1. So I want to say that the answer is 1, but I'm also going to carry out another 1, and that goes to the next column over. So I've got my answer, that's 1, my output up here, the output's 1. And I've got this carry out here, this is carried out to our next column, the carry out, that's also 1. So now I've got my complete truth table here for all combinations of A and B in our carry in. And I've got the cases in which carry out fired, and I've got the cases in which the output fired. So this is very similar to the PowerPoint that I gave for, I had an X and a Y and a Z as inputs, and I had an output 1 and I had an output 2, and I tailor-made that so that you would be able to go back to that example and refer to it for purposes of making our 1-bit adder. So we can actually use that example. We've got our truth table now, and now we want to make a 1-bit adder circuit from this. And so we're going to make a sum of products expression here. Specifically, we're going to make the canonical form of our sum of products expression, and remember that that just means that it's as hairy as that expression will ever get. We can't make it any messier. So we can actually use Boolean algebra if we wanted to simplify that canonical form expression a bit. But we're not going to do that. We're just going to provide the original canonical form, and we're going to build the circuit strictly based off of that. So we want to look at carry out. So this is our first output here, and we want to just look at the cases in which carry out fired. So I've got this case here where it fired, and I've got these 3 cases here where it fired. So I've got 4 cases in total where this output fired. So I can go ahead and I can make a mathematical expression to represent this. So I could say, let me do this in a different color. I could say carry out, C out, is equal to, wherever there's a 1 here, I want to look at what the state was for the inputs that caused that output to fire. I really care about when this output fires. So I want to look at the state, and I see that A was set to 0 when this fired. So I want to invert that. If you refer to the tutorial, you'll know that when we have a 0, we want to invert that. So I've got A, and I got to turn that into A naught. So I've got A naught, and then I have times, and then I want to look at the next bit here when that output fired. I look at the next bit, and I notice that B is set to 1. So it's okay. I can just bring B down. I can bring B down directly here. And I have B times, and I look at the next bit. I'm going to abbreviate C in. I'm going to abbreviate that to just C. So we've got a 1 here, so I can just bring that down directly as well. So I've got A naught times B times C, and that covers the first product here in our sum of products canonical form expression for this output here where this bit fires for our carryout. And since this is sum of products, we have to add them together. So we go into our next product here. We go into our next case where it fired a 1, and then we look at our inputs here, and we see that A was set to 1, so we can bring that down. And we have times. We look at B next, and we see that B is 0, so we got to invert B, so that becomes B naught. And then we have times, and we look in that row, and we look at the next input, and we see that C, well, that was set to 1, so we can just bring that down directly. So we have A times B naught times C. And for the final exam, make sure that you write the negation with a hat over the top of the letter. So you might see this represented a number of different ways online. You might say you've got A prime. This is one way of representing negation. They have A prime with the caret at the side of it, and that's the same as saying A naught with a hat over the top of it. That's also the same as some of the examples you might have seen on Moodle where we have A naught, and it's represented with this dash next to it with this strange thing hanging down off the side of it. That's all right. That's A naught as well. And you might also see in some of the written examples, we might say not A. We might say this. We might say not A, and that also inverts. A. So you might see any 4 of these represented online or in textbooks. So, but for the final exam, we want you guys to use the notation where you have the hat over top of the letter. So please be sure to practice this so that you're in the habit of it for the final exam. And then we also want to represent, we want to be very explicit when multiplication is happening here. So I could have just as easily written A times B times C. I could have written that as A naught times B times C. And this is just as correct. It represents multiplication, but we want you guys to be very explicit about representing that there's multiplication happening here. So just be sure to write this dot in between the characters where you have multiplication happening. Just be very careful to remember that for the final. So these are our first two products, and we go to our third product where the carry out input fired. So we look at our third case here where it fires, and we look at the states of input, and we look at A. A is 1 and B is 1, so we can just bring those down directly. So we've got A times B, and then we've got our, this is our third input. We've got our last input bit here, C. C is a 0, so we've got to invert that. So we've got times C naught. And then we've got our last product here, our last case where it fired, and we look again and we see that, oh no, it's not this row, it's this row. This is our last case here. This is our last case here where it fires. So A, B, and C are all set to 1, so we can bring them all down. So I've got A times B times C. And so this is our final sum of products expression. And we'll be using this to create our circuit in Logisim. So I'm going to exit full screen here, and I want to bring this. I want to bring one note to the side for a second, so I can use this mathematical expression in Logisim, and I'll go ahead and make a 1-bit adder circuit for you guys. And so in Logisim, we want to go. We want to right-click on Untitled. We don't want to hit File New. We don't want to do that for making another circuit. We want to be able to still use it here, and so in order to do that, we have to right-click on Untitled here, and we click Add Circuit this way. So I'm going to say that this is a 1-bit adder, and I've got our 3 inputs. I've got input A, so I'm going to take an input pin. I'm going to label that input A, and then I've also got input B. So I'll go ahead and label that input B. And then finally I've got our carry in. And so I've got that down here. So I have carry in. And so I want to take these input lines and I want to extend them very far over. And I can use this in our circuit. So these are our input lines for A, B, and our carry in, and I want to extend them and make our not lines as well. So I've got our not lines coming out here, and I make them a not line by adding a not gate. So that's our A not line and our B not line, and here's our C not line. And I want to go ahead and extend these out as well. And I want to bring these far out so that they can be used in our circuitry. And you'll see why in a second why I've extended them so far out. So I've got all my lines. And so now I've got my first AND gate. And I want to go ahead and orient this south here so that it's easier to use. And so by default, you'll notice that Logisim has got 5 inputs coming into the AND gate. And this is not the number of inputs that we'll need. Notice that we've got a bunch of products occurring here. But each time we've only got 3 inputs. We've got A and B and C, and these are all being multiplied together. Remember that AND gates are multiplication and OR gates are for addition. So we definitely want an AND gate here since we're multiplying these 3 numbers together. But we don't want to use the 5 input lines that Logisim gives us by default. We only want to use 3 since we're only dealing with multiplying 3 numbers together. So this is our first gate. And we can go ahead and label this gate. Since this gate represents A naught times B times C, so it's a good idea to label that in Logisim. So I'll just say not A times B times C. And so now I've got this label in case I make a mistake later on, I can go and refer back to it. So I've got not A, so I just bring that up to our This is our A input, and this is our not A line. And so I just bring that into our gate here. And then I want to hook it up to, this is not A times B times C. So I just hook up the last two lines to B and to C. And so now I've got these connections coming into the AND gate, and whatever the output is of this AND gate, that is the product of not A times B times C. And so now I can go ahead and make a second AND gate, and I bring that over to the side. And the second one should be for the product A times not B times C. So I go ahead and change the label of that AND gate. So A times not B times C. So I bring in A. So we've just got our standard input line for A. And then I've got not B. This is B's input line. This is B's negated input line, our B not line. And then we've got our input line for C. And so now our second AND gate's done, and now I bring our third AND gate over. And I go ahead and I look back at our mathematical expression. I say, well, what was the third product? Well, we have A times B times not C. So I go ahead and I change the label for that gate. So A times B times not C. Let's see. Yes, A times B times not C. So I extend the lines. I've got A times B times not C, and that product is done. And now I have the final product here, A times B times C, for this last product right here. So I just go ahead and I create an AND gate since I'm multiplying A and B and C together, and I change the label and say A times B times C. And I just want to go ahead and hook up our lines here. I hook it up to our A line and to our B input line, and then I hook it up to our C input line as well. And so now I've got our four products here. And notice in the order of operations, we want to perform, by the order of operations, we want to perform multiplication before we do addition. And so that's why we've come up with these products. That's why we've piped everything into an AND gate. Before we've dealt with the addition here, we've got our products here. We've got our products 1, 2, 3, and 4. We've got the answers for all of our products. So now we can deal with addition. Now we can deal with, let's sum the answers of all these products together. So we had a 3 input AND gate because we were multiplying 3 numbers together in each of these cases for each of these products. But our OR gate will be a little bit different. We've got more than 3 inputs coming into our OR gate. Notice here that we've got these 4 products, and we're adding them. We're adding each of them together. So this is going to be an OR gate, but it's going to have 4 input lines coming in for each of the products. And then the output of that OR gate, that'll be the final output for our whole mathematical expression. That'll be the final answer for our sum of products, and that'll be the final answer for our carry out bit. So if I go ahead and I set up an OR gate here, I can set up an OR gate. I'll change that to 4 input lines, and I'll orient that south here, and I'll just hook all the lines up. So I've got this input line, and then I've got this input line coming in, and then I've got this one coming in as well. And then now I've got the final input line coming into the OR gate. And so now our 4 products are being summed together, and I've got some output. So this is the carry out bit for our sum of products expression. And notice again that Logisim is set this to 3 state. We want to change this to no. We don't want this to be in 3 state. We want this to be just a binary bit, 1 or 0. This is a 1-bit adder. So this is just our carry out. So we look at our original truth table, and we saw this mathematical expression was for our carry out expression. This was a carry out expression for our sum of products. So that's what this bit represents when this fires. So now we've still got 1 input left to go. We've still got to represent our output bit. So if we go back to OneNote, We go in here and we want to represent and look at when the output fires. So we've got this case and this and this and this. We've got 4 cases again where this fires. So we have to write a mathematical expression. So we say our output. I'll just write this in blue so it's a little bit different. We've got our output is equal to, well, this case it fired when A was 0, B is 0, and our carry-in was 1. Well, let's look at what we need to write in our sum of products expression. Well, A is 0. We need to invert that. So we write A naught times B is 0 as well. So we write B naught times our final number. Our carry-in, that's 1. So we can just bring that down directly. We can bring down C. And we have plus. And we look at the second case where it fired, and we say we have 0, 1, 0. So we want to have A naught, B, and C naught. So we have A naught times B times C naught. And then we have our second, we have our third product here. So the third case in which our output bit fired, and we've got A was 1, so we can bring down A. And B and C, those were 0, so we need to invert them. So we just bring down A, and we multiply that by B and C, which we invert. And now we've got our final product here, our final case where the output bit fired. And it fired when A and B and our carry-in were all set to 1, so we can bring all of them down. And so now here's where you might notice if you've got a careful eye, well, this term here at the last end, that's the same as this term here from another expression. And given the knowledge from our previous video, given the knowledge that gates are done in a feed-forward manner, and that we can use their lines wherever we want without modifying anything, we could actually take the output for our gate, for our carry out for A, B, and C. If we look at our gate here, we could take this output line and we could use that in our output expression. We could go ahead and use that for simplifying things, and we'll actually save on an AND gate. We won't have to compute this again since we've already computed the expression A times B times C. So for our output expression, we'll go ahead and use that. But we've still got to write the gates for the rest of our expression. So we've got A naught times B naught times C, and that's going into our first AND gate. So I want to set up an AND gate, and so I've got not A times not B, and I've got times C. I think that's correct. Yeah, not A times not B times C. And so I want to hook up A naught and B naught, and I want to hook up C. And so now I've got my first product here. And I look at our second product, and I've got A naught times B times C naught. So I'll add a gate. I have not A times B times not C. I think that's correct. Yeah, not A times B times not C. So I hook up not A, and I hook up B, just our standard B line, and then I hook up not C. And so this gate's done. And now I've got only one gate left, since we're going to go ahead and reuse that A, B, and C output. I've only got one AND gate left. So I have A times not B times not C. So I go ahead and I set up an AND gate, and I've got A times not B times not C. Now I'll go ahead and I'll move that to the side so that the comments aren't quite so overlapping. And I've got A, so I'll go ahead and hook that up to our A line, and then I've got not B, so I'll hook that up here, and then I've got not C, so I'll hook that up here as well. So I've got this AND gate and this AND gate, and we want to add them all together now. We want to add each of these products together now, and we also want to add it with the result of this gate as well, because we're using A times B times C, because we use that in both products here. So when we create the sum for our final output, since this is our canonical form expression, this is our expression for our output, we want to sum each of these four together. So we want to use a OR gate. We're dealing with addition here. So we hook up all of our lines. We got this added to this and this, and we have our final product here that's added, and then the result of this, that is our output for our 1-bit adder. And so now we've got circuitry. We've got a 1-bit ALU in Logisim. So this is a complete 1-bit adder. Our circuit has all been done. So one of the things that you can do now, you can go ahead and use this, and you can't use it directly in your ALU. We still have to make this and chain it together and turn it into I'll be turning it into a 4-bit adder for my example, but you'll be chaining together several of them to make a 32-bit adder. So before we do that, I want to go into this chip design feature. See this second button right here? If we click on that, that allows us to design the chip. So we go ahead and we scoot this out of the way. And so we click on this, and we see it's a port. And if we look down in the lower right hand corner, we'll notice in blue it's highlighted the input in our circuitry that port corresponds to. So this port happens to correspond to number A for our input. So in the built-in adder for Logisim, number A goes at the top. So I want to go ahead and make our chips work exactly the same as Logisim's chips. So I'll just put A at the top, and I look at this port, this next port here. If I can click on it and highlight it, I notice that in the lower right hand corner, highlighted in blue, is our second input for number B. So I know the built-in adder in Logisim, number B, the input is the one on the bottom. So I go ahead and put that there. So I go ahead and I look at this last input. I know that that's my carry-in. So in Logisim, if we go ahead and we look at our main circuit here, we have our carry-in, that's at the top. So if I do our adder and we're designing our chip, we want to put our carry-in at the top here. And then we've got our two outputs here. Here's an anchor. We'll just put that aside for a second. We've got one of our outputs here. This is the actual output. This is the answer. And if you look in the right hand corner, it's the output that is on the right side, and that is our output. That is our answer. That's not our carry out. That's our output answer. So in Logisim, that goes on the right. So we just put that there. And then this last one, that's our carry out, so that just goes on the bottom. So if we drag the box of the circuit, the box of our circuit chip here, we can adjust it to fit our new circuit that we've created, and we can take our anchor here and we can move it down. I'm not sure quite what this anchor is for, but Logisim seems to have it set in the corner, so I move that down there as well. Now I take this extra curve and I delete it. I don't need that. So I've got our 1-bit adder chip, and if we look at our main circuit here, we can click our 1-bit adder and just drag, and it brings us a chip that we can use, and it looks very similar. Look at how similar it is to our built-in adder chip. And we've got our input A, our input B, we've got our carry in at the top, we've got our carry out at the bottom, and then we've got our output answer. So it's very similar. It's our 1-bit adder chip. We're doing well so far. So now we want to chain several of these together. We want to make a 4-bit adder. So I add another circuit. I call it a 4-bit adder. And you can go ahead and you can go straight to a 32-bit adder if you'd like. So I want to go ahead and I'll add 4 of these together in here. And now we've got this module, we've got these modules for individual columns for addition. Imagine that we're adding binary by hand, and we've got a 4-bit number that we want to add together. So we've got a 4-bit number, and we say that that is number A. Let me move that over a bit. We have number A. And so we want to add that to, say that we want to add that to number B. And these are both 4 bits. And then we want some output. We want some output. We don't want it in 3 state. We want some output, and that's just our answer. And so we've got our 1-bit adders here. So here's where it ties in everything that we've been doing as far as modularizing things in our expression. So back in OneNote here, when we were looking at an individual column and we said we had A added to B, and we had some output answer, and then we had a carryout, which went to the next column. So the carryout for this column, this carryout, got piped into the next column as the carry in for that column. So like looking at this expression here, we've got 1 and 1, that's 2. We represent 2 as 1, 0 in binary. So 0 is our answer, and then 1 is our carry out for this column. 1's our carry out. And that gets piped all the way into our next column over here to the carry in on that column. So 1 gets set to the carry in over here. So just imagine all of the carry outs for all the columns getting piped into the carry ins for the next column. So for example, if this is our first column and we've got our carry out here, we want to go ahead and pipe that into the carry in for our next column. And we'll go ahead and do that for all of our 1-bit adders here. And so now we've got everything hooked up together. And we still got to worry about overflows. Remember how I said the leading bit indicated whether an overflow occurred? So this last adder, you'll always have the last one indicating the overflow bit. So this will tell you there's always just going to be 1 bit. I'll change it out of 3 state. So we hook this up to our last adder here. And this is always going to tell us whether or not an overflow has occurred. So if we look back at our expression and we add, here's a 4-bit number, and I want to add it with another 4-bit number, and I get an answer, but these numbers were too large, and I happened to get 5-bit answer, and so I had some overflow bit here. This bit was turned on, indicating there was an overflow. And so since that was the last bit, that's the last bit coming out for the carryout for our last adder. So this is our overflow bit. So this is how the hardware detects an overflow, and we'll be using this in our ALU. And so also keep in mind how we said we've modularized this, and we were adding a number A and B, and we had a carry in. And even if we didn't carry in a number, we did have a carry, and it was just 0. So the carry in for each of these columns, those were all set to 0. So what we've got going on here, for our circuit in Logisim, since there's nothing hooked up to this line, this carry-in needs to have a static bit, a static input bit, that's just always set to 0, so that the circuitry will work. So if I bring this down into our, if I bring it down into our circuit, we should be all right. So this just sets up our first carry-in. So now our circuitry is set up correctly. Now we can start piping in our numbers for A and B. So this is our first column. So we want to take this very first bit in number A and pipe it into the number A port for this adder. And we want to take the very first bit for number B and pipe it into this port. And then we take the second bit for number A and we pipe it into this port, and then we take the second bit for number B and we pipe it into this port. And then we keep going for the 3rd bit and the 4th bit and our 4-bit number here. And we always pipe the number A bits into the top port, and we always pipe the number B bits into the bottom port. So we go ahead, in Logisim we've got, in the wiring column we've got a splitter here. And I'll go ahead and I'll orient this south here. So I can use this splitter if I hook it up to number A. I can use it, and if you notice, our splitter complains of incompatible widths. So we want to go ahead and change it to a 4-bit splitter. And so we've just changed all the 2s to 4s. By default, they give you a 2-bit splitter. So if you look at the splitter, you'll notice very tiny numbers at the top. And so if we hover over one of the pins, it says, oh, this is bit 0. So that represents this first bit in our number. And this is bit 1 and bit 2 and bit 3. And so bit 0, that goes into our first column for addition. And bit 1, that goes into our second column. Bit 2, that goes into this column. And bit 3, that goes into our next column. And then we do the same with number B. We want to use a splitter. We hook that up to number B. And we take our first bit here and we pipe that into our first column. And then we take our next bit here and then we pipe that into the next adder for our next column. And then we take our 3rd bit here and we pipe that into our 3rd adder for our 3rd column in our expression. And we take the last one here and we pipe it into the bottom port. And so now we've got our numbers A and B, and it's got fed into our 4-bit adder. But we haven't dealt with taking the output. So we're gonna have a 4-bit output here, and it's gonna come out a splitter. It's gonna come out in the opposite direction. So, whoa. Okay, let me just add a separate splitter here. So I've got some 4-bit splitter. Let me set it up right here. Let me put it in this orientation. So if I hook it up to our answer, and now I've got the bits coming in. So this is output. This is the output from our first column, and then here's the output from the second column and the third, and so on. So I want to match these up exactly to our splitter in the exact correct order. So here's bit 0, bit 1, bit 2, and so on. So I hook up bit 0 to our first circuit here, and to our second circuit I hook up the next bit, and to our third circuit I hook that up to our splitter on the third input here, and then I hook up this last one to our last adder. And so now I've got a 4-bit adder, and everything should work now. If I want to add two numbers together, let's add together 2 plus 1, and that should give us 3. And if we look at our output, we get 3. Now let's go back in. I'll try the same example for you. 1 1 1 1 plus 1 1 0 0. I have 1 1 1 1 plus 1 1 0 0. And notice the output is 1 0 1 1, but we've also got an overflow. A hardware error occurred. So 1 0 1 1 plus the overflow. So if we look at our handwritten expression, we've got 1 0 1 1. So the answer is correct. And then we've got this last overflow bit. So we're able to now, our hardware is now able to check if we're trying to perform addition that's too large for the number of bits that we have here. So when you're doing 32-bit addition, you've got 32 bits to work with. That's a lot of addition bits, but you've still got room for an overflow if you try to enter numbers that are too large. So the hardware is able to handle that case now. It's able to handle that error and pass that on to the programmers now. So say you've got something in your program where you try to divide by 0. That would be an example of like a hardware error. And so that would get passed back to your program, and you might have a an exception, it would say, oh, you tried to divide by 0. So you would see that, and your program would handle it. And this all happens on a very low level in the hardware. And it's able to detect that for us and handle these expressions so that strange things don't happen. And by strange things, I mean that it actually detects this error and it doesn't just go ahead and foolishly add these numbers up and tell you, oh yes, this is the correct answer for sure. It's able to tell you that it had an error. It's very nice to be able to know that this was not the correct answer, so that we're able to handle this expression. So now we've got our 4-bit adder chip, and we want to use that in our main circuit here. So if we go in and click on our 4-bit adder and we drag it over, we notice that it uses the default the default chip scheme in Logisim. So we've got our inputs on one side and we've got our outputs on the other. But we've got to redesign this chip again. We've got to go in here for our 4-bit adder. We've got to click on this option so we can design our chip, and we can make it look like the built-in adder for Logisim. So this is our carry-in. This is our carry-in here. So that goes at the top. And this is our 4-bit number A. So that goes at the top here. And then we've got our 4-bit number B, and that goes at the bottom pin. And then this pin right here, that's our carryout. So that goes at the bottom of the chip. And this is our, here's our anchor. This is our output and answer. So that goes on the right. So then we can drag the boundary of the chip. We can drag that onto our inputs to make it actually look like a chip. We can put our anchor on here. Let's just scoot that over to the side just a bit. Okay. Let's delete this curve, and now we've got our 4-bit adder chip. So now we can go back into our main circuit. We can click our 4-bit adder, drag it over here, and now we can start using this in our ALU expression. We've got our very own adder chip. So we just drag this into place. Now we can start using our own adder chip. So remember our opcode for our ALU, that was 000 for addition. So I'll just go ahead and adjust the ALU so that we're doing addition here. And then remember that in order to get our adder to work, we always have to carry in a 0 to get it started. So we still need this static 0 coming in to get the ALU started. And then once we've got that going, then we can perform addition. So I can add a bunch of numbers together. Say I want to add 2 and 2. So I've got 2 for number A and 2 for number B, and I should get 4 as the answer. So if I look at our output is 4. In binary, 1, 0, 0 is 4. So everything seems to be working correctly. If I try another example, I try 2 plus 1. Well, that should be 3. And if I look at our output, we've got 1, 1 is the answer. So that does give us 3. So we know that the ALU is functioning perfectly using the built-in adder chip that we created from scratch. So I hope this video was helpful to you. So in the assignment, in order to get full credit, you will want to use this and create not a 4-bit adder, but you'll want to be creating your own 32-bit adder and using that inside of a 32-bit ALU with all of the arithmetic instructions for all of the 8 opcodes that are defined in the assignment. So good luck, and I hope this was helpful.